I've run NASA's Advanced Technology Development Program for years and years, and we did a lot of light scattering work. We did bulk scattering. What we did was we took small rooms full of equipment and moved them into shoebox sizes so we could fly them in the space station. We're now doing experiments with those kinds of devices and with other things like that to look at how order arises out of disorder in nature. And I've given other talks on that, and I can talk to you about it later. Today I'm mostly going to focus a few slides on the hardware just so you know it's real. And then I'm going to mostly spend time talking about the GUI, and then you can ask me questions about how we do certain things, because the GUIs are fairly multi-level, and there's some tricks you need to know to pull things off. And I'm sure you'd all figure them out, but I just wish somebody had figured them out before me. So I'm more than happy to tell you where the piles of hair are and whatever else you'd like to ask about. So what we're doing here is we've built the light scattering instrument. We spun off a little company. Back about 4 years ago, NASA decided they were going to go to the moon and Mars and forget about science. Well, that all changed in the meantime. But while that was happening, people like myself were told that, you know, you might be driving taxis. So I got together with my friends. We spun off a lot of these patents and stuff we had. And we licensed this stuff. We added a bunch of stuff. And fortunately for people out on the street, we're not driving taxis. So anyway, we developed a next generation of light scattering hardware. Hardware that would particle size from nanometers to microns. What we did was we added a laser beam feedback into the detector so it acts like a superheterodyne radio. So you get all this gain from superheterodyning by beating against your light signal. And you can get considerable gain up to about the level of the shot noise in your laser. So that allows us to look at 1 nanometer protein, stuff I haven't seen before. And you know, usually it's hard to see very dilute solutions of that. Let me put the concentration and the size work together. It allows us to go to very concentrated systems because now we know some tricks on how to not see the multiple scattering. But in doing a big task like this, there's just too much for one person to do. And either of us in this project could have built hardware or designed software. And my colleagues did the hardware, and I'm working the software. They're both almost complete. Oops. This is a box of the hardware. The little test tube you see, it's teeny. This design will actually work with suspended drops and on platens with hundreds and hundreds of drops. Here's just a close-up of a 40 nanometer vial. We're just shooting a laser beam into it, and we're looking at the backscatter of it. And this is okay. And that's just a picture to show you that we have something real. This is how the whole technique works when we do bulk scattering. We also do surface scattering. But for bulk scattering, as the particles dance around in solution because they have temperature, the interference that comes from those particles all combines and it forms a speckle. And that speckle fluctuates based on how fast the particles dance. And how fast the particles dance depends on how big they are. So we get an absolute measurement of diffusion, and we get resolution of like 1 part in 10 to the 12th because we correlate. Now, as for what you do with that information, if you believe in spherical chickens, you can stuff it into the Stokes-Einstein equation and back out a particle size. And there's some other things you can do. But thanks to Mathematica, we can actually look at systems that are fairly ill-conditioned and hopefully separate out multiple stuff that couldn't be done before. And I'll show you what our hopes are there. So here's some real data. This is fairly recent, and it shows we've extended the range into very, very weak solutions and into very, very concentrated systems, and you can see the different particle sizes. But the basic message is we have a huge dynamic range with this instrument. It's non-invasive. You can make measurements in less than a minute. We're using avalanche photodiodes, which are 90% quantum efficient. Photomultipliers are 15% quantum efficient. We have ways of compensating for the DC offset you get when you add a local oscillator. We know how to do that without saturating detectors now. And when we correlate, correlation will pull signal out of noise at about 120 dB level, which means if I'm standing next to a jet airplane engine, it's running full throttle, and you whisper in my ear, I hear you clear as day. And if a signal's sliding around in stochastic, but there's periodicity in it, it doesn't average out. A correlator will lift that out. There's lots of cool stuff you can do with correlators. In fact, we're building a correlator which used to be the size of this small wall, and it's on an FPGA chip, field programmable gate array. You drop it in, and then all your hardware, which now takes milliseconds to drop into as a software program, runs at hardware speeds. So now you can do nanosecond time slicing with a piece of software. You want new, improved software, like we're moving from linear correlation to fractal correlation. We don't have to spend $100,000 every time we burn a new ASIC mask. We just rewrite the code and drop it in. So we're using an analog input to these digital correlators. And that allows us to deal with DC offsets, lots of other things. I guess I should go back and say, the interface has a very simple input because ultimately we want it to be commercial, but it also has other levels. It has a more sophisticated level and an advanced level for like an academic user that would want to know real answers and not just whether it's green or red lights saying go. So this is our simple input, and basically it has a start and stop button. And if you look on the left, I don't know if there's a laser pointer, but on the left you'll see I could probably just use the mouse. You'll see a little pull down. And I actually have the program running, and if I have time I can show you it running, but you can pull down all kinds of things. You can run hardware, you can run software to synthesize raw data, you can pull up old data files, you can synthesize data files using quantum principles so that you have real noise that's lumpy and shot noise that's grassy. So this will tell you, I'll tell you more about that in a minute. But what this basically has is it has a screen that shows you decaying exponential if you've got a system swimming around in there, if you have any particle size. This is your signal coming in, just a small snippet of a much vaster signal, but you just want to know that you're not clipping it. You want to know you're within a usable range. And if you want, on this simple screen, you can click the little box in the upper left-hand corner, and that will show you a power spectrum of what you're looking at. And that's not really useful if you're dealing with exponentials, but if you're doing surface light scattering or you have a shifted local oscillator, then what you get is an exponentially decaying cosine. And what this power spectrum is a shifted Lorentzian, and the center frequency tells you things, and the half width, half height tells you things. And I'll be happy to tell you things about that later if you want. So as you saw, I just popped in another window. When I popped in this power spectrum, we do lots more of that, and you'll see in a few slides how we do it at many different levels. But the easy way to do it is to take a pick command and say, which of these many possible things do I want to use right now and display for you? But the thing you need to know if you go to use a pick command, a take command, and things like this, is that if you pick of a string, it evaluates everything inside the array first, and then it picks. And that's not real efficient if you've got really complicated things. So what you want to do is wrap a hole around each of the elements. And after talking to the gurus at Wolfram here, I found out that there are easy ways to do this. I mean, I was trying to there were some ways that don't work. But what I was doing was wrapping hold around each individual element, picking, and then doing a release hold. There's other clever ways you can do it. If you try to map hold, like you see here, that won't work. You'll see it evaluates and it just gives you the answer before it picks. But what you can do is you can map hold with an unevaluated, and that will work. Or what I've learned from Lou the other day was you can use extract with an unevaluated, and extract has a third command out here, which you can wrap a hold, and that will work. I wish this third command existed for a pick, but maybe someday. Yeah, sure. It holds these, it tells them not to, like these. Here it keeps them in this form. It's 1 + 1 + 1. It's uber hold, you're right. That's what it is. It really holds it as telling you it holds it. It only tells you it holds it, yes. You can also, and Brett showed me this other clever way of doing it where you take a function, you can wrap it in such a way that it doesn't evaluate. So anyway, there's a number of ways to do it, but the basic message is, if you've got sophisticated graphics and lots of it, and you want to pick which ones to display, wrapping a simple trying to map hold isn't going to cut it, but you do want to hold what you've got, and there's lots of good ways to do that. Here's a more sophisticated version of what you saw, but now what we're doing is we're allowing the user to see fit results. So like say if they tell the program they want to see the first two cumulants, they want to know what particle size they have, this says, these are the particle sizes, this is the cumulant you selected, it turns blue, it says it's the second cumulant up here, and this allows you to pick what you're looking at. So you can actually scale it. It turns out if you're looking at real data, if you're dealing with things like local oscillators, the lines get flatter and flatter and higher with bigger offsets. You rescale it, it always looks nice. So we built in commands like rescale. We crop from the left and right so you can pick which channels, because a lot of times the zero channels where your noise is, and there'll be this huge spike. So we just crop that out. So these are things that aren't built in, but they're easy to add, and I can show you. And then we track all this, and as we load different kinds of parameters and different kinds of things, these all change. They all change dynamically, and I do that with a pick command, and I'll show you that in a second. Here's the more sophisticated level that you would never show up just a regular user, but if you're in academia, you would love to have the ability to do things like fit a double exponential. Well, this happens to be single exponential data, and I told it down here to fit a double exponential, and if you look closely, before I rescaled, you'll see these were numbers like 10 to the 8th, but the second fit it tried to find was like 0.2. So Mathematica is pretty good when you use constraints at knowing what's right and what's wrong, and I'm going to show you some condition numbers and stuff in a minute to figure that out. But this is a constrained fit in data set A. And we added constraints, and I'm going to show you a little bit about how we did that. So I built a GUI that takes and just color maps this data. So you rescale it between 0 and 1, you color map it, you take the log of it since it's an exponential, then you take the gradient of the log. And if the gradient's one color, you've got one exponential. If it's got two color blobs, you say, you know, I can move this little pointer back and forth here, and where I set it, if it separates into two color blobs, that'll say, this exponential, you guys look on the left, you guys look on the right, you know what, the guy on the left's a lot bigger, usually you'd both want to go there and tell me that same answer. By using constraints, I can force them to go to separate areas. And I can also do more sane things, like say there's no such thing as negative mass, the second moment is positive, just things you know from physics. So it's very helpful, especially when you're dealing with noisy data. So this is the kind of stuff we're doing by adding constraints. And you can see we can add local oscillators in different amounts. If we're, in this case, there's different amounts set, we can look at them. Let's see this chart, okay, that's the same. This is just a graph showing you that in the case when you have two sets of equations, it tells you this is the equation you chose to fit, so I chose that bogus set of two exponentials. It actually symbolically prints it. You just tell the fitting routines, I want to see what the symbolism is, you put it up, you say I want to see what the constraints are, you put them up, so the user can just check this tab and look. And it's really nice to have all these things kind of walled off by tabs, because what the tabs do is they say, dynamic that's looking at all this stuff in the GUI, don't look in the tabs unless it's being used. And that saves the dynamic from sweeping through lots of code that just wastes time. Now, if you've got a vertical height that's adjusting and it's not fixed, then tab will look through it anyway. So what you need to do is inside your tab statement, you put a little wrapper that says, you know, if this is not the tab number that's selected, stay away. And that will keep you from only looking at the portions of code that are useful to you. And it'll make your front end really snappy. If you want to make your front end really drag, it's certainly possible if you don't use some of these tricks. This is the constraint tab. Basically, you see I split this into two sections of exponentials. When I move that marker, it did it. I can also set it by hand. And I can set all the other parameters with sliders and stuff. But basically, it's just a cute way to set constraints if you want to do really fancy stuff. And I'm just showing you the fancy stuff because you're here at a Mathematica conference. This is stuff that's really nice to see if you really know the theory behind it, and you look at these correlation numbers and you see like 0.9, 0.9, 0.9, you say, oh, a double exponential is not a good model. Those parameters are strongly correlated. That means they're not independent. We better try a different model. So it's really nice to have this feedback. And another thing that is nice, and I'm hoping it's a feature in the future, is to look at the condition number to see how good your model is. And that condition number is easy to calculate. You just take the Hessian and ratio the eigenvalues and max them in. This is the tab that does data synthesis. You can set what kind of decays you want, how much local oscillator, all of this stuff, but it synthesizes data using a random number generator in a nice way that tells you how long you need to run. Basically, it tells you the sweet spot for an experiment. So you set up all your parameters for the experiment, you synthesize the data, you say, yeah, no, we're not going to see what we're looking for if we try this. And you try something else. And this goes back to that standard old maxim, which I really love. 100 hours in the lab will easily save an hour in the library, which applies for data synthesis as well. So you can do with computation now what's much harder to do in the lab. Here's just an example of some 3D plots from the synthesis. We can actually make these bigger or smaller, but you can see this is some of the analytic results as a function of local oscillator. And you can see what the local oscillator does to your noise. And you can tell whether you want feedback or not. And it's a really good teaching tool. This tells you what the residuals are like. In this case, I think we're comparing the old secret relation with something we've generated now, which is more realistic based on quantum, with quantum noise. Because the noise, it turns out, correlates channel to channel. And you don't see that when you use a very simple model. This is just the last tab. And what the last tab does is it allows the user to automatically save data sets so you can walk into the lab, start it up, and leave. So it just takes the date and the time. You can prepend something to that file name and postpend something if you want, and then just leave, and it just starts saving stuff. And it also lets you do funky things like change the background colors and important things. All right. This is just to show you that if you want your code to run fast, it really helps if you modularize it. So I have lots of modules, and I'll show you a flowchart of that in a second. But like if I pull in data set A and I pull in data set B to compare the two from the different sides, so I have a separate fitting routine for the different cumulants. I have 4 different cumulants that run in parallel table for data set A, 4 that run in parallel table for data set B, and they're running on different kernels. The input streams and the exports, those are separate kernels. So basically all these things are just different packages, and I just send them off, and they can all run at once, it doesn't matter. But you can see I have several different cores up here, and I can run them all at once, as long as the license in Mathematica allows it. When editing modules, I found that there's lots of things in the packages that were hard to edit. So if you just did a select all, and actually this was a call to tech support whining, I said, I can't believe how hard this is. It's got to be easy. Tell me I'm stupid. And they said, well, we won't tell you that, even though no, they said they actually called back a couple hours later after they went and researched it. They said, because I wasn't writing in Workbench. I was writing in native Mathematica. And Workbench, I guess these issues go away. But if you switch from code format to input format, you get line wraps and all this stuff, and stuff doesn't go off the edge of the page. You can do all the editing you want, switch back to code format so it runs at high speeds. And that was really a valuable trick that I didn't see anywhere, and I was happy to learn it. Here's just kind of a layout of how the code flows. I told you we separate it all with tabs, so you only look at each tab one at a time, and we even do inside of the tabs, we do separate parts that we look at one at a time, and if that tab is set, we use setter to pick and extract out which portions to show on the screen. Same thing over here when we're looking at the data synthesis parameters versus the graphs. We can use setter to pick out which batches we want. We've got a block of dynamic code that sets up the GUI. It also talks to the inputs. It talks to the fitting routines, does all that in parallel, looks at the non-dynamic stuff. So basically, modularize, modularize, modularize. Make blocks of code that don't need to be seen unless you need them. Here's a trick that it's kind of a workaround. When you write large blocks of code, and in this case we can look at different data sets and we can give them the same parameters or different parameters and compare how the setups are. One of the things we needed to do was write little notes in there to ourselves. And when we would go to write notes to ourselves, if I can get my cursor here we go, we would find that those notes took a while to write. So if I come into this little box, oh, I'm sorry, I'm telling you the next page. Let me go back. You saw how when I set up all of the little boxes and the grids on the screens, the thing that would destroy that in an instant or a heartbeat would be when the screen goes to extend itself because I need more space, if you could move the scroll bar left or right. And I didn't see it in the documentation, but John Fultz showed me this really neat trick where you can lock the horizontal or the vertical position of the scroll bar simply by wrapping this pane in a dynamic module and then making one of the elements so that it refers to that second part, in this case the vertical. So I can actually, here, I'll look at it, let me just show it to you. It's easier to show than to tell. So here's a system that's generated. See how I can make this bigger or shorter, but I can't go left or right. So we've actually just locked the horizontal size but not the vertical size, and that turns out to be very useful in keeping your layout so that it's controllable. The next thing I was going to tell you about was one of the things that was a pain for me was when I go to enter text into that input field so I can take little notes. It turns out if you have lots of text to enter in, if you're doing it in like a single input, it's fast. If you're doing it in some huge program, it really crawls. So the easy way out of that is just create it so that when you touch the box, it brings this up. And then you can do whatever you want. You can just, as fast as you can type, it'll come in and you hit it. And you come down here and it'll come, and there it is. It's right in your text field. So that's kind of a workaround for now, but it's the only thing I found that was, you had to have this kind of trick, and then it makes everything else workable. The other kind of thing that's kind of funny, and this is a Microsoft feature, not a Mathematica problem, is that if you're programming in Windows rather than Mac or Linux, and you've got multiple GUIs like I have, if you do anything that's computationally intensive, it'll swap the order of the windows. And what Microsoft is doing is what Ian calls shimming. So they ghost that window so that it doesn't become rogue and trash their machine. They don't care the fact that you're trying to run two GUIs. They just want their machine, their operating system to be stable. So I find that what I have to do is I make it so I can pop, if I have a wide screen, I pop one GUI next to the other and it's not a problem. If I have a short screen, I make it so it pops up and then you close it and you just make it so it's easy to pop up all the time. But it stops that window swapping order. And that's just a feature from Microsoft, and I don't know how to get that changed. So we've had a lot of good help from the folks in tech support, from the developers, just from a great team of people here. And I'd like to help if I can too. If you have any questions, just ask me.